after class on Monday, Ben asked a couple of clarifying questions about the conversions that we're doing. And Ben had some familiarity when he had learned in a previous course that there's an equation that looks like this that people use in the way we were using the equation in class on Monday. And scientists use this for dilutions, and that's really common in lab where scientists will make up a solution, and it's a high concentration stock solution that's just on their shelf, and it might be 2 molar glucose. And what we're going to learn about is that third thing I described in knowing about molarity is that there would be a recipe. How do you make up a 2 molar solution of glucose? And so we'll learn how to make it. We could make all these, and then in practice, what scientists often do is they'll have a stock solution, and then over time, they can use that to make up whatever working dilutions they need. So for example, you might need a 100 millimolar glucose solution. And so that's what we mean by a dilution equation. And we, although it's done a lot in a research lab, we won't talk about this too much. However, we'll be doing this, and it's pretty logical and natural. And so I want to plug dilutions into what I talked about in class. And so I'm going to go back to this equation that I use, and all I've done really is I've solved for whichever one of these is the unknown. And so we're going to put the unknown there, and it's going to have a number and units, and then we're going to have a ratio over here, and it's going to have a number and units, and we're going to multiply it by another number that has units, like that, okay? Shouldn't have that like that, probably, okay? And so here's a great example of this use of this equation. It's used in a variety of different settings. Here's one. It's a recipe in a kitchen. You want to double the recipe. And you know, just from practice, that you would take each ingredient and you multiply it times 2. You could cut cut a recipe in half, and you'd multiply it by every ingredient by a half, like that. Okay, and so and so this is the equation that you're using when you do that, and I'll just start putting this in so you can see in this example. And again, we're not doing recipes here, but it's just a good example because you kind of know how to do this intuitively, and this is how you do it in a more rigorous manner, right? Okay, like that. So in the recipe, it could call for a cup of flour. And you say, for each ingredient, you say, well, I want to double the recipe, okay? And so what should I put in here? Well, let's say the recipe calls for the ingredients to make up 1 dozen cookies. And you want to double it, you know you want 2 dozen. That's why you know you want to double it, because you have an outcome, a yield, that you want to get. You want to get more cookies than that, twice as many, or 10 times as many, like that, okay? And so what you're doing when you double a recipe is you're saying, well, the recipe calls for 1 cup of flour. The first ingredient is 1 cup flour. And I want to know how many cups flour should I use. And you can see already that this fraction is going to be 2. And the way it gets to be 2 is you're going to put the amount of cookies you want, 2 dozen cookies, into this fraction, and you're going to put the original amount, yield, 1 dozen cookies in. And what you're doing there is you're putting a unit over a unit, and 1 over a 1 in math always can just be canceled because it's just 1. And so these units I've crossed out, they'll cancel. And you go from 1 cup of flour times 2 divided by 1 equals 2 cups of flour. And you just do that for each ingredient. And that kind of use of this equation is called generally scaling. So in like a big factory, scientists can scale up, right? They can have a small operation and they want to scale up. And so they do this scaling. Or they're like, okay, we don't want to waste these expensive ingredients, we're going to scale down like that. So it's scaling. Here's another example of scaling that you already know about that's very sensible to give you a feeling for this. And I think the key thing to think about is that we have these 4 values, and they include both units and numbers like that, okay? And so the units are actually really often very helpful in determining where to put these, right? And so let's just look at this for a second. Notice that, this unit here is going to be this unit here. We want to know how many cups of flour we want. And so we want to take this side of the equation and do something to it to get to this unknown. And we could increase it or decrease it by, a multiplication factor, okay? Then here's another thing to say about it, and notice that this is true of this equation, that as this goes up, this will go up proportionally. These values are said to be directly proportional. So let's just say, oh my gosh, you better double check. Actually, when you look back, the original recipe called for 1.5 cups of flour. And as you increase this value, you're going to increase this value. To double a 1.5 cups of recipe, you're going to use 3 cups here. So that's what directly proportional means, is that as this value goes up, this value goes up. As this value goes down, this value goes down. And that should make sense, right? When you move over to the cinnamon, it's just 1 teaspoon like that. Well, I guess that's a different part. Just as you scale up and down, these values go up and down together. This value also is directly proportional. So that value is also going to be directly proportional. This is how many cookies you want. And as the amount you want goes up, this value should go up. As the amount you want goes down, this value should go down. This value is said to be inversely proportional. And that's the original amount. And that's the original recipe. Now, if you said, I want 2 dozen cookies, you know that's what you want for your party, and you look at the recipe, well, if it's 1 dozen, great. But if it's half a dozen, the original recipe, then you're going to need more, right? So instead of multiplying it by 2 over 1, you're multiplying it by 2 over a half. The final value is actually going to be 4 cups of flour if the original recipe calls for 1 cup of flour for half a dozen cookies. So as this value goes down, this value goes up. So let me just get another color in here to show you that. So for both these values, as it goes up, your answer is going to go up. For this value, as it goes up, your answer is going to go down, inversely proportional. And so that should make logical sense when you think through it. And when you're confronted with a question, sometimes it can really be helpful to organize the units and then organize the units and the numbers to have the proportionality match the what the goal is. Okay, so let me erase this, and so it's very good to think about the logic of a math equation, always. And so let me just write it again, and this time what we're going to be doing is we're going to look at a map. And so this is something that folks are still familiar with, although Google and GPS are kind of starting to reduce our familiarity with the map. But it's an old paper map, and there's a legend. And in the legend, it shows that 1 inch is equal to, say, 2.4 miles on this map, right? Like that. And so you have this thing where you're like, okay, well, how far is it to our destination? And you've taken out an old ruler, and you measure the approximate distance, and you say, the distance we have to travel is 3 inches. How many miles is that, right? So in this case, we're going to be going from this, where this is going to be our answer, is going to be miles, like that. And we're going to start with 3 inches. And that's interesting, right? Because in this case, we have a mismatch, right, between our units. So in this case, we are converting our units. That's what we were doing in class. That's what our questions about the the homework for Unit 1 are about. It's going to be a unit conversion. We want to go from inches, we're starting with inches, to miles. And this is good though, because you can see that the more inches on the map, the more miles that would be equivalent to, right? Like that, as those increase. So that should be directly proportional. We already have decided it should be either here or here. It should not be there. Okay, so then what about this? And this is again the scaling relationship, but in this case the units don't cancel. So it's a scaling relationship and also a unit converting relationship, like that. So in this case, what we're going to put in is that we want miles out of this, and so we're going to put in that 2.4 miles is equal to 1 inch. What we're doing here is we're just multiplying this value times essentially 1. These are equivalent, like that. Now let's just think about this, right? As the map changes its scale, right, the more miles there are per inch, the further the distance would be when we travel 3 inches, right? On the other hand, if this decreased, the miles that were traveled would be more, like that, right? And so that looks good. Now, notice this too. In this case, when we multiply this out, we're going to have this 3 times 2.4, so that's going to be 7.2 miles. That's going to be our number. But what about these units? And the answer is C. We put this on top partly because these are the units we want coming out on top. And then this is going to be an inch, and this is essentially in the numerator of a fraction, and this is going to be an inch. We're going to get inch over inch, and those will cancel. So our math here in this scaling, using a map is doing 2 purposes for us. It's not a unitless fraction. It has these units, and we're using those and that scaling to calculate, to make a number calculation, but also a unit conversion, like that. Now, because that m1 over m2 equals v1 over v2 is a dilution, let's just look at a dilution. And so let's just say that we start out with that 2 molar solution of glucose, and we want 100 millimolar. So we have a working stock of 2 molar solution, and we want to dilute it down to 100 millimolar. Okay, so the next thing is, you see there's only 2 numbers here. What do the other numbers want? Well, 1 is going to be our question, and that's the volume. How much of this should we use? How much of this should we get out? We're making 100 millimolar stock, like that. And so that's going to be our question. How much volume do we use? We can pipette out, 10 mils, 50 mils. How much do we need? And the answer to that is going to be, so we're going to want a number in volume. And so that could be milliliters, like that. Okay. And so the answer, then the next thing is, what's our 4th number, or our 4th, value, right? We have these 2 values and 1 unknown value. And so we have to ask, and we ask, how much of that do you want? You want a 100 millimolar solution, but how much? Do you want a milliliter? Do you want a liter? Like that. And so that has to be asked not as part of the calculation in our question and getting the answer, but just up front. They have to tell us how much volume you want. So we're just going to put up here that our answer is how many milliliters do we want to use, like that, okay? And you can start to get a hint that it makes sense. This is where that value is going to be. it's going to be, well, how many milliliters of the final solution do you want? So we have to ask the person who's asking for the solution, how many milliliters of the solution, the final solution, do we need? And let's say they want 1 liter. Well, 1 liter is a different unit than milliliters, so off to the side, we're going to have to convert liters to milliliters because we want to plug in the comparable units here. And 1 liter is equal to 1,000 milliliters, like that. Okay? All right? And so then this is going to be sensible because we asked and they said we want 1,000 milliliters. We want 1 liter, 1,000 milliliters. So as this volume increases, if they wanted 2,000 milliliters, this would be directly proportional. So that's looking good. We could still worry that maybe that value should go there, but it should go either here or there because it's supposed to be directly proportional. It should not go down here, right? So we're fitting in these numbers, and now we can fit in these 2 numbers, right? And what it is saying is that we have a solution of 202 millimolar, 2 molar, and we will drop it down to 100 millimolar. So once again, we have to make a unit conversion. We will just change this to molar to millimolar. And we could do that conversion, and we were learning about that in class. And this would be converted to 2,000 millimolar, like that, okay? Now, we can just think about this, all right? So as we decrease the molarity of the solution we want, the volume would decrease as well, right? So if we said, I want 100 millimolar, that would be a certain number of milliliters. If we just wanted 50, we'd need half as many milliliters, right? So this should be directly proportional. That 100 millimolar should go up here, and the 2,000 millimolar should go down here. And you see what's going on here is a dilution is, again, like a recipe. That first procedure of making the 2 molar glucose solution is like a recipe. We're going to weigh out some glucose powder. We're going to dissolve it. And then we're essentially making a recipe. We're scaling a recipe here. So you can see these units are going to cancel, and this one will come through. And that's why we need to have these units all match up. So if they don't match up, we have different concentrations here. We need a conversion to make sure the units match up. And so that's a first step in preparing this equation, is making sure all these units will match up. Now, notice this, that if we had a higher concentration stock, if it was 4 molar, well, we wouldn't need as much to get this solution, right? So as this goes up, that value goes down. So it's inversely proportional. So all this checks out. And that's really what a scientist is doing in their head to set this equation up. And it's just like all of these examples are like somebody gets familiar with that and they just can do it in their head. They might have to use a calculator or computer to do the math, the multiplication, right? Because sometimes the volumes are like 1,258 milliliters, something like that, So sometimes the math numbers just need to be crunched through some computerized help. But setting it up is based on reasoning. And it is a little bit of a kind of mystery whodunit task, because you have to figure out, well, there's going to be one value we want to get that we don't know, and then what are the other values? And we found 2, and then we're like, wait, we need a third value. What is it? And that's, well, how much of this do you need? How much of this final solution do you need? Okay, great. So just talking through that, we don't have to become super experts at this. It's just great to see this, because it's a great way of appreciating how math is just a tool like that. Okay, great. So thanks for watching this, and bring questions to class. The homework for Unit 1 is not due for a while, and so we'll be able to talk about this in class, as well. That'll be great. Okay, awesome. Thanks.